Inheritance and cleanup. When using composition and inheritance to create a new class, most of the time you won't have to worry about cleaning up. Sub-objects can usually be left to the garbage collector. If you do have cleanup issues, you must be diligent and create a dispose method, the name I have chosen to use here. You may come up with something better for your new class. And with inheritance, you must override dispose in the derived class if you have any special cleanup that must happen as part of garbage collection. When you override dispose in an inherited class, it's important to remember to call the base class version of dispose, since otherwise the base class cleanup will not happen. The following example demonstrates this. Each class in the hierarchy also contains a member objects of types characteristic and description, which must also be disposed. The order of disposal should be the reverse of the order of initialization, in case one subobject is dependent on another. For fields, this means the reverse of the order of declaration, since fields are initialized in declaration order. For base classes, following the form that's used in C++ for destructors, you should perform the derived class cleanup first, then the base class cleanup. That's because the derived class cleanup could call some methods in the base class that require the base class components to be alive, so you must not destroy them prematurely. From the output you can see that all parts of the frog object are disposed in reverse order of creation. From this example, you can see that although you don't always need to perform cleanup, when you do, the process requires care and awareness. Exercise 12.3, modify exercise 9 so that it demonstrates the order of initialization of the base classes and derived classes. Now add member objects to both the base and derived classes and show the order in which their initialization occurs during construction. We initialize the base class first, starting with the member objects in order of definition, then the derived class, starting with its member objects. Also note that in the above example, a frog object owns its member objects. It creates them, and it knows how long they should live, as long as the frog does, so it knows when to dispose the member objects. However, if one of these member objects is shared with one or more other objects, the problem becomes more complex and you cannot simply assume that you can call dispose. In this case, reference counting may be necessary to keep track of the number of objects that are still accessing a shared object. Here's what it looks like. The static long counter keeps track of the number of instances of shared that are created, and it also provides a value for ID. The type of counter is long rather than int, to prevent overflow. This is just good practice. Overflowing such a counter is not likely to happen in any of the examples in this book. The ID is final because we do not expect it to change its value during the lifetime of the object. When you attach a shared object to your class, you must remember to call addref, but the dispose method will keep track of the reference count and decide when to actually perform the cleanup. This technique requires extra diligence to use, but if you are sharing objects that require cleanup you don't have much choice. Exercise 13.3, add a finalize method to reference counting.java to verify the termination condition. See the initialization and cleanup chapter. Exercise 14.4, modify exercise 12 so that one of the member objects is a shared object with reference counting, and demonstrate that it works properly. All types of rodents share one member object. When we instantiate a new concrete rodent, the reference counter of the shared member is incremented. When a rodent is destroyed, the reference counter is decremented. The shared member is automatically disposed after release of the last reference,